Liquefaction of gases is a critical phenomenon. So in this lecture, we'll discuss the liquefaction of gases as a critical phenomenon from the unit states of matter. How the gases can be liquefied, which conditions need to be maintained to liquefy the gases, which parameters need to be set to liquefy the gases. Simply, it is nothing but the how to convert the gaseous states into the liquid state just by changing the temperature and pressure. Okay, we'll discuss in this lecture. That is liquefaction of gases, critical phenomenon. So as we have discussed, by lowering the temperature and increase the pressure, gases can be liquefied. What happens at lower temperature? The gaseous molecules, they will lose their kinetic energy. We know that during the properties of the gaseous states, we have discussed that as the temperature is increased, what happens? The kinetic energy amongst the gaseous molecules, it will get increased, and due to this, what happens? Due to the increasing the kinetic energy of the gaseous molecules, what happens? Expansion is takes place. So as by increasing the temperature, expansion is takes place due to the increase in the kinetic energy in the gaseous molecules. So definitely, as if you reduce the temperature, if you decrease the temperature of the gas, what happen? The gaseous molecules, they will lose their kinetic energy, and due to the loss of kinetic energy, what happens? These gaseous molecules, they will try to become a stable. Okay, whatever their random collisions, as per the kinetic molecules theories of the gaseous molecules, they are moving in the random motions. Okay, these collisions, these random motions, that Brownian motions, it will be get reduced. Okay, this all these random motions or the Brownian motion, this is just due to the kinetic energy of molecules. But if you have reduced the kinetic energy, as you have decreased the temperature, what happens? Due to loss of kinetic energy, the gaseous molecules, they will try to get settled. They will try to become a stable. So due to this, what happens? These gaseous molecules, they will try to come together. Okay, this is the effect of the temperature on kinetic energy of the gaseous molecules. And as the kinetic energy decreases, means what happens? They will move. Their motion will be in the slow. Either slow or they will get settled. So due to this, what happen? The small aggregates, small coalescence of the gaseous molecules will be takes place. And due to the coalescence, the gaseous molecules, they will bring together, and their attraction between the gaseous molecules, it will be increased. And you know that if the attraction between the molecules, if it is there and they are living together, they are staying in the group together, these are the properties of the liquid. Okay, in gases there is a no attraction between the molecules. They are stay apart from the each others in the gaseous state. They behave as a disperse, they behave as separately at a large distance in the gaseous state due to the kinetic energy. But exactly here, by reducing the kinetic energy, what you are getting here? Aggregates of the molecules. Not only aggregates of the molecules, along with the aggregates of molecules, what you are getting here? We are getting the attraction between the molecules. We are getting aggregates, we are getting the attraction between the molecules along with some fluidity. That is aggregation, attraction, forces between the molecules and the fluidity, all these properties of the liquid state. So what happened here? The gaseous molecules, they have start to show, the gaseous molecules, they have start to behave as a liquid state just by reducing the temperature just by decreasing the temperature. Due to decrease in temperature, what happen? Kinetic energy, it is lost by the gaseous molecules. Same effect will be observed by increasing the pressure. What will happen by increasing the pressure? As you are applying the pressure, as you are increasing the pressure on the system, definitely what happen? It will get, as it will get compressed, volume it will get decreased. As volume it will get decreased, what happens? The gaseous molecules, they will come together. Again aggregation will be formed. Again forces of attraction, it will be more as they have come together. The distance between the molecules as it is decreased. Okay, the gas molecules come closer by compression and co-oscillations to form the liquids. Okay, this is the basic phenomenon and basic concept in the liquefaction of the gases is decrease in temperature and increase in pressure. Okay, and this phenomenon, due to change in the temperature and the pressure, due to the decrease in the temperature and increasing the pressure, whatever the behavior of the gaseous molecules they are showing, okay, that is pressure temperature conditions phenomenon, it was put before to us by the scientist Andres in 1869. He has studied the pressure temperature curve, okay, in the process of liquefaction of the various gases. Okay, understood. What happened due to decrease in temperature and what happened due to increase in pressure. Okay, and how gaseous molecules they will get liquefied. And this Andrews established the, for every gas there is a temperature. Okay, by studying the relationship between the temperature and the pressure and studying the liquefaction phenomenon at various temperature and pressure, he concluded that, he observed that a specific temperature is there below which the gas can be liquefied. Okay, as you are decreasing the temperature, the you are getting the minimum temperature. At that minimum temperature, the gases can start to liquefy, and below this any temperature we can set, at any temperature gases can be liquefied. All the gases they behave as in a liquid state, and that temperature is known as the critical temperature. But above that temperature gases cannot be liquefied, no matter how greater pressure we are going to apply. Okay, you have to set the minimum temperature, or while decreasing the temperature we will reach to such a temperature, such a point. At that point and below that point, what happen? The gases they will behave in the liquid state, and the such temperature is known as the critical temperature of the gases. Okay, so we will discuss about the definition of the critical temperature. Critical temperature is just simply means it defined as the temperature above which it cannot be liquefied no matter how great the pressure applied. Okay, what it means? It is the temperature below which what happens? The gases behave in the liquid state, and above which gases cannot be liquefied no matter how greater pressure we are going to apply. If the temperature of the system is higher, if the temperature of the gas is higher, what happens? Kinetic energy it will be there. So what pressure, at what extent greater pressure we are going to apply, it will not get influenced that much. Okay, because the molecules they will behave, the molecules they will move in the random motions, so that they will not get aggregate. So along with temperature, what happen? The pressure is the very, very critical parameter in the liquefaction of the gases. So first critical parameter is critical temperature. It is the temperature below which gases can be liquefied and above which gases cannot be liquefied no matter how great pressure we have applied. Okay, and it is denoted by the TC. Next critical parameter is critical pressure. So what is critical pressure? It is the minimum pressure which is required to liquefy the gas at critical temperature. So means temperature is the very important parameter in this case, because we have to focus, we have to concentrate on the temperature. From the definition of the critical pressure, we can clearly get idea about the critical phenomenon. It is totally related to the, basically it is concentrated, it is focused on the critical temperature. And whatever the temperature we have set as the critical temperature, and at that critical temperature for the liquefaction of the gases, how much pressure it is required. Okay, at the critical temperature, how much pressure which is need to be applied to liquefy the gases, it is known as the critical pressure. It is not telling that at a critical pressure how much temperature is need to be applied. It is not like that. Okay, temperature you have to set must be critical, and to liquefy the gases at that critical temperature or below that critical temperature, whatever the pressure it is required, we need to consider. Okay, so what is the definition of critical pressure? The minimum pressure which is required to liquefy the gas at its critical temperature, and it denoted by the TC. So at a critical temperature and at a critical pressure, whatever the volume of the gas, okay, whatever the volume of the gas which are shown by the gas, it is known as the critical volume. Okay, that means critical volume, it is simply the volume occupied by a mole of the gas at critical temperature and critical pressure, and it is denoted by the Vc. So it is nothing but critical temperature, critical pressure, and critical volume, that is Tc, Pc, and Vc. These all are the critical constant of the gas. Okay, and all real gases have the characteristic critical constants. They have the critical temperature, they have the specific critical pressure, and they are showing, they are occupying the specific volume at the critical temperature and critical pressure, so that they have the critical volume at the critical temperature and critical pressure. Okay, so that critical temperature and critical pressure, what happen? The gas, they will start to show the identical behavior as like liquids. That is nothing but at the critical temperature and critical pressure, what happen? The gases, they start to behave. The gases will start to show the properties and characteristics of the liquid state. And that state, that situation, at what the gases start to show, the gases start to behave as like liquid, it is known as the critical state, because it is indistinguished. It is not easy to identify whether this material in the gaseous state or in the liquid state. Okay, so that situation is critical, and that situation, that point is known as the critical state. And the submerging of this gas into the liquid, conversion of the gases into the liquid, it is known as the critical phenomenon. So critical phenomenon is the simple, at the critical temperature and critical pressure, the gases will convert, gases will merge into the liquid state, gases molecules will start to show or will start to behave as like the liquid state. State, that situation, that condition is known as the critical phenomenon. Okay, understood what you mean critical phenomenon, and what are the temperature, pressure, and volume at that critical phenomenon, that critical state. It is known as the critical temperature, critical pressure, and critical volume. So to convert the gases into the liquid, or while studying or while understand the concept of the liquefaction of the gases, you should have to understand the critical phenomenon. And to understand the critical phenomenon, you should have to understand the effect of the temperature and pressure on the gaseous state. And you should have to understand the what is critical temperature, what is critical pressure, and what is critical volume. Okay, this is overall about the critical phenomenon, that is critical temperature, pressure, and volume. So, and by considering this critical temperature and the critical pressure, the scientist Andrews has plotted the graph of the temperature versus pressure. And whatever the graph he has plotted the graph of the pressure and volume because temperature is critical. Okay, and that Andrew demonstrated the critical phenomenon in gases by taking the example of the carbon dioxide as one of the gas. And what she had did here, he had just plot the curve of pressure and volume of a gas at a constant temperature. And the plot of pressure and volume at constant temperature, it is known as the isotherm or isothermal. Okay, when the temperature is the constant, and whatever the plot you are getting, it will be the isotherm. So in this case, the pressure volume curve which was plot at constant temperature, and that plot, that curve is known as the isotherm. So simply, how you can get the isotherm, that is isotherm of an ideal gas at constant temperature T, that is the C, pressure and volume at the temperature is the constant throughout the systems. We can at any point temperature is constant, so it is called as the isotherm. Let us see, as you are increasing the pressure, see initially at pressure is low, we are getting the more volume of the gas. As you are increasing the pressure like this way, we are getting the volume is less, that is decreasing the volume. Okay, so this isotherm, that is due to the increasing the pressure, how volume of the gas is changed. And as the volume of gas due to the compression, okay, it is get reduced. And we have discussed earlier what will be happen on the intermolecular distance, what will be happen on the intermolecular forces of attraction. And Andrews, what he did, he has plot the pressure volume curve of the carbon dioxide. Okay, that is in the form of Andrews isotherm of carbon dioxide at various temperature. He has taken the various temperature, and at this various temperature, what he did, he had plotted the curves of the pressure and volume, and it is known as the Andrews isotherm at constant temperature. Okay, we'll see what he did. This is the Andrews isotherm of carbon dioxide at different temperature. He has plotted the carbon dioxide and the pressure volume relation curve at 0 degree Celsius, 21 degree Celsius, 31 degree Celsius, and 50 degree Celsius. That means he has taken the various temperatures while plotting the relationship between the pressure and volume. Okay, let us see here. This IH, it is just behave as like this ideal gas isotherm. Okay, at 50 degrees Celsius IH, whatever the curve you are getting, it is just behave as like a ideal gas isotherm. It is not showing the any fluctuation. Okay, whatever the curve here, we are getting isotherm of the ideal gas at the constant temperature. The same curve, same isotherm curve you are getting here in the IH at 50 degree Celsius. So what Andrews did, they have categorized, he has explained the behavior of the gas at three different temperature. Initially what he did, he has explained the behavior of the gas about the 31 degrees Celsius. Okay, about the 31 degrees Celsius. So we have taken the example of the 50 degrees Celsius. So what happens at this 50 degrees Celsius, whatever the curve isotherm of ideal gas we are getting here, it is behave as like a ideal gas. So all other isotherm above 31s, okay, thus in the regions they will behave, they will exist in the gaseous state. So afterwards, he has considered one more conditions, that is isotherm below 31 degrees Celsius. Okay, the isotherm E of G, it is showing at 31 degrees Celsius. So A B C D curve, it is showing the isotherm below 31 degrees Celsius. So what happened exactly below 31 degrees Celsius in this isotherm A, B, C, D? Okay, at 21 degrees Celsius or the any temperature below the 31 degrees Celsius. That curve, it is divided again into A, B, B, C and C, D. First we will discuss about the curve A, B. Okay, let us see here. A, B. Here at the point A, volume of the gas, what is the volume of the gas? It is more. Okay, at point A, as the on a x-axis we have taken the volume. So as we'll have increased the pressure here, okay, as you have increased the pressure, what happened? You are getting the slightly reduced into the volume. Okay, when the curve is moving from the A direction to the B directions, what we are getting here? Decrease in the volume of the gas as you have increasing the pressure. So what happened at point B? The volume is suddenly decreased. Let us see here. At point B, we are getting the decrease in the volume. So what did it indicate? It indicate the just formation of the liquids, because we know that the volume of the liquid, it is less than gases. Okay, so at point A it is showing the greater volume, and as we have increased the pressure from A to B, we are getting the sudden decrease in the volume due to the increase in the pressure, and at point B we are getting the low volume. Okay, that is sudden decrease in the volume, and that it will be the sudden decrease in the volume, it will be the indication of what? Liquid state. So what we can say that at point B, what happened? The carbon dioxide, it is converted into the liquid form. Okay, understood what happened from A to B? As pressure increased, volume decreased, and volume decreased, it is the indication of the liquid state. Okay, the carbon dioxide, it has started to behave as a liquid. So again, if you consider the curve of BC, okay, it is an horizontal curve BC. If you consider this horizontal curve BC, you are getting the, it is a just a stagnant line, just a straight line. Okay, we are not getting the any variation. Okay, in the isotherm BC. Okay, it is a just a horizontal line BC. So what did it indicate? Pressure is remains constant, because we know that increase in the pressure volume is decreased. But exactly what here happened? Pressure is constant. And due to the pressure is constant, what happened? What will happen here? The liquefaction, it will be continue. Okay, liquefaction, it will be continue as we have maintained the constant pressure. Okay, and at point C, let's see here. At point C, what you are getting here? All gaseous molecules, all gas, which is converted into the liquid. Okay, from B C curve, we are understood that at constant pressure, okay, the gaseous molecules they have liquefied, and at point C, all the gases they have get liquefied. And to due to this, what we are getting here? Again, sudden loss, sudden decrease in the volume of the gas. Okay, from A to B, what happens? The gases they have decreased the pressure. Sorry, due to the increase in the pressure, the gases molecules they have getting the decrease in volume. And at point B, whatever the volume, due to the sudden loss in volume you are getting here, it will be the indications of the liquid state. And from B to C, as the pressure is constant, what happen? The gases it will start to convert into the liquid. And at point C we can say that all the gases it is converted into the liquids. Why? Because let's see here, whatever the curve CD we are getting here, whatever the curve CD you are getting here, it is a vertical. Okay, this vertical curve, this vertical isotherm of the carbon dioxide, and it will not vary. It is not showing again any plateau. It is just a vertical. So that what you can indicate from the curve CD, you may increase the pressure, but there is no change in the volume. Not that much change into the volume of the gas. Okay. So what it indicate? As you increase the pressure, we are not getting the variation in the volume, we are not getting change in the volume, and we know that this is the sign, this is the indication, this is the property of the liquids. Because if you increase the pressure, if you compress the liquids, we are not getting the any chance to reduce the volume of the liquid, because liquids are not compressible. Gases are compressible, liquids are not compressible. So in the curve CD, in the curve or isotherm CD, as we have increased the pressure, whatever the volume you are getting, it is remains constant. There is no any chance to further compressibility of these molecules or of this state. So it will be indication or it will be sign of the liquid state. So from the isothermal CD, we can say that gases have liquefied. Understood? The isothermal A, B, C, D. What happens exactly at A to B, B to C, C to D? At point B, what happens? At point C, what happens? And what curve or isothermal CD? What will it indicate? So we'll discuss about the one more condition, that is the at 31 degrees Celsius. Okay, that is the isothermal E, F, G. Let us see here. Isothermal E, F, G. So in the isothermal E, F, G, okay. So as the critical temperature of the carbon dioxide, it is at 31 degrees Celsius. Okay, so above that 31 degrees Celsius, there is no possibility of the conversion of the carbon dioxide into the liquid. So from the isothermal EFG, at this temperature 31 degrees Celsius, what are the points we are getting at the F? It is called as the critical temperature of the carbon dioxide. So what you can say that critical temperature of carbon dioxide is the 31 degree Celsius. And at this temperature, 31 degrees Celsius, whatever the isotherm, that is the whatever the pressure volume curve we are getting, EFG, it is called as the critical isotherm of the carbon dioxide. So in this EFG curve, what will happen? The portion EF, okay, the critical curve EFG or critical isotherm EFG, the portion EF is there. What will indicate? It is represent the pressure volume curve of the carbon dioxide. Here, EF is the pressure volume curve of the carbon dioxide and FG is the pressure volume curve of the liquid. So why? Let us see here we are getting the more volume at EF region. Okay. And from the point EF to the from the point G, we are getting the less volume or decrease in the volume. So what happened at point EF? Exactly what happened at point EF? The curve records the twisted conditions. We can't conclude at the point EF whether this carbon dioxide in the liquid state or whether the carbon dioxide into the gaseous states, because right hand side of the this point EF, that is the EF curve, it is behaving, it is showing the pressure volume curve of the carbon dioxide gas. Left hand side of this point EF, that is the isotherm FG, it is showing the pressure volume curve of the liquid state. So at point EF, it is not easy to distinguish, it is not easy to identify exactly which state or which properties which are behaved or which are shown by these molecules. Okay, this critical situation, the situation is critical. We can't distinguish easily in which state the carbon dioxide is behaving. Okay, so as the corresponding pressure is called as the, so that we can call it, this point AP is called as the critical point. Okay, and whatever the pressure at this critical point F, it is the critical pressure of the carbon dioxide. Whatever the volume at this point F, it will be the critical volume of the carbon dioxide, and temperature is constant, so it will be the critical temperature, that is 31 degrees Celsius. And this pressure volume relationship which was shown by the isotherm EFG, it is known as the critical isotherm. So what you can say from this picture, or what you can conclude from this EFG curve beyond the F? Okay, beyond the F or this curve FG, that is the vertical axis, it is just parallel to the liquid curve. We can say that it will be just a boundary between the gases and liquid curve. So again you can say that from the point F, that the point F is now for us here for in this carbon dioxide isotherm, point F, it will be the critical point. So simply we can say that right side of this critical point F, the carbon dioxide, that is curve EF, is showing the gaseous state. Left side of this critical point, that is the FG curve, it is showing the liquid state. Okay, this conclusion we can get from this isotherm. Okay, understood what is the Andrews isotherm and how the carbon dioxide it will behave or shows the different properties at the different temperature, and how we can conclude about the critical isotherm, that is the critical temperature, critical pressure, critical volume and critical points, and how the gases it will be converted into the liquids from this Andrews isotherm. Okay, this is overall about the Andrews isotherm. Next, by using this Andrews isotherm and the critical temperature, critical pressure, how we can convert the gases into the liquids. So there are methods for the liquefaction of the gases. Okay, so what is necessary to convert the gas into the liquid? Very first is the gas need to be cool. At what temperature? Below the critical temperature. Okay, we have to carry out the cooling of the gases below the critical temperature with the application or with the add of the adequate pressure which is required to liquefy that gases below the critical temperature. Okay, so depending on the methodologies or depending upon the techniques or the ideas which are used to attain the lower temperature, okay, or to attain the critical temperature, or techniques which is used to attain the temperature below the critical temperature, the methods for the liquefaction of the gases which are available. So out of these various methods, we'll discuss the three important methods here. By these three methods, how the temperature which is attained below the critical temperature and how the liquefaction of the gases is carried out. First method is Faraday's method. Second method is Lind's method. And third method is the Clouds method. So in Faraday's methods, the cooling which is carried out by just by the freezing mixture. We'll discuss how it is. Second, Lind's method, which is in which compressed gas is used and that compressed gas it is released with the help of the narrow jet. Okay, it is totally depends upon the Joule-Thomson effect. Third method is similar as like Lind's method, but in this Clouds method, one additional facility is provided. That is the mechanical work done, which was carried out by using the gaseous molecules. So we'll see first about the Faraday's method. Let's see here about the Faraday's method. Okay, in this Faraday's method, he has used one tube, and through this curved tube, what you the basic principle of this Faraday's method is he has used a freezing mixture. Okay, so in this vessel, whatever the blue color crystals we are getting in this vessel, we have taken the ice. Okay, and it is mixed with the salts. Okay, that is the freezing mixture. And we know that the ice melting, to melt the ice, we need to provide the energy. Okay, to melt the ice, temperature is utilized, heat is absorbed. Okay, that is, it is the endothermic process. Okay, energy is required to melt ice, that is energy is absorbed, heat is absorbed, so we can say that the endothermic process. So heat is required to melt the ice, and along with he has used the salt. For salt also it is again endothermic process. There also temperature, thermal energy, heat is required. So exactly this concept. Okay, so for melting of this ice, as the temperature is required, so why can't we provide the temperature from this glass tube? Okay, we'll see how. What he did in the tube, he has taken the some reactants and he has provided heat through this substance reactant mixtures. So what will happen due to this reactant substance, they will convert it into the gases. Okay, no matter which reactants we have taken, it will be depends upon the which gas which is required to you. If you need the carbon dioxide, we have to take the reactant from which we are getting the carbon dioxide as a product. Okay, so such types of the reactants she has taken, scientist Faraday's, and he has provided temperature. So as the reaction it is proceed, what will happen? We are getting the gas. And if this gas is passed, let us see. As this gas is generated, as this gas is evaporated from this heated mixture, definitely the gas it is in hot form. Okay, already it is having the temperature. So it will reach. Okay, As this gas is reached to this point where it is surrounded by the freezing mixture. So what will happen? Whatever the temperature, whatever the thermal energy which is present inside this tube due to the gaseous molecules, it will be absorbed. Okay, it will be absorbed by this refrigerating mixture. So that what will happen? By absorbing, by uptaking the thermal energy from this tube, the ice mixture, this refrigerating mixture, it will start to melt. So what exactly happening here? This ice mixture, it is absorbing the thermal energy or the temperature from this gas tube. Okay, that means exactly from what? From the gaseous molecules, the thermal energy it is absorbed by the refrigerating mixture. So what will happen? The gaseous molecules they will get cool. Okay, cooling effect will be observed into the gaseous molecules. That means what happens? The temperature of the gaseous molecule it will be reduced. That means what happens? Kinetic energy of the gaseous molecules it will be reduced, and the gaseous molecules they will start to aggregate. They will start to show the intermolecular forces of attractions. Okay, and they will start to behave as a liquids. Why? Because whatever the temperature, whatever the thermal energy which is absorbed by this refrigerating mixture due to this loss in kinetic energies takes place inside the tube, whatever the gaseous molecules which are present. Okay, these concepts, these methodologies which are given by the Faraday's, this is quite simple. Okay, in 1823. So whatever we have discussed, it is mentioned here. Just I will read here. Used freezing mixture of the ice with various salts for external cooling of the gases. Okay, the ice mixture or refrigerating mixture it is not directly added into that tube. It is surrounding to that tube. So next is the melting of ice and dissolution of the salt. Both are endothermic process. That means heat is required. Heat will be absorbed. The temperature of the mixture is lowered up to the temperature when the solution becomes saturated. Heat gas liquefied. Okay, gas reactant Faraday succeed in liquefying the number of gases such as sulfur dioxide, carbon dioxide, nitrous oxide, chlorine by this method. We have discussed how cooling is takes place and how liquefaction is carried out. So that Faraday has employed just V-shaped tube in one arm of which the gas was prepared. That is by using the reactants, which gas which is required on that basis. We can choose the reactant, we can provide the temperature and we can proceed that reaction. And from this reaction, whatever the gas we are getting, we have to pass this gas to the V-shaped tube from the one end to the another end, and in this other arm the gas was liquefied under its own pressure. Okay, here we are not going to apply the any pressure. The pressure of the gas it will be on. That means the gas is liquefied by this at their critical temperature. It is just near about the ordinary atmospheric temperature. Okay, whatever the ordinary atmospheric temperature is there, either below or above, but it is near to the ordinary atmospheric temperature. There is not that much difference between the critical temperature of these gases, and the such gases we can convert into the liquid formed by the Faraday's method. Okay, so this is about the Faraday's method. Simple. That is, we have to provide the cool, we have to withdraw, we have to remove the thermal energy from the gaseous molecules. That is, as we are removing thermal energy, we are withdrawing the thermal energy. That is, we are reducing the temperature, means we are reducing the kinetic energy of the gaseous molecule. And this is attained by, this is done by providing the freezing mixture surrounding to the V-shaped glass tube. Okay, in the Faraday's method. So we'll discuss about the second important method is Lind's method. Okay, the Lind's method it is depends on the Joule-Thomson effect. Okay, see the constructions or the apparatus for the Lind's method. In this, whatever this chamber we are getting, it is the expansion chamber. Okay, so in this expansion chamber, the spiral tube it is provided in the zigzag direction or the spiral direction, that is the spiral glass tube, and to this spiral glass tube the inlet from the external it is provided through which gas is carried out. Okay, that means the expansion chamber is there. In this expansion chamber the spiral tube is there, and the spiral tube it is attached to the external inlet through which gas is provided. Here the refrigerating liquid it is surrounding to this glass tube through which gas is carried out. Okay, and this gas or the air which is supplied through this spiral tube it is from the compressor. Okay, here the one compressor is there. We'll discuss about this. And at the end or at the tip of the this spiral tube we are getting this narrow opening, just a small opening. We can say it is a narrow jet. Okay, so we'll discuss one by one. Here compressor is there. Here we are getting the compressor. Through this compressor what happened? Fresh air is supplied. So why it is necessary to provide the compressed air? Why not the simple or the as usual air we are getting from the environment? So we'll discuss as we are providing the compressed air. Okay, in compressed air, when the compressed air it is released, okay, when the compressed gas it will get released, or when the compressed air it is released, what will happen? It will show the cooling effect. Why it is showing the cooling effect? Because in the compressions gases molecules they are compressed, they are in the together, and at from these compressed molecules, as the molecules which are living together, and if they get sudden expand, that means sudden expansion is takes place. So whatever the attractive forces which are present in between the gaseous molecules in the state of the compressed gas, okay, they are carrying the somewhat energy, they have the somewhat attractive forces, and when they get sudden expand, this means what happen? These attractive forces they will get break. The breakdown of attractive forces between the gaseous molecule will be takes place when we are carrying out the sudden expansion of these gaseous molecules. So what happen? As the sudden expansion in the gaseous molecules takes place, we need to overcome whatever the attractive forces. Am I right? And to overcome the whatever the attractive forces which are present between the gaseous molecules, we need to provide the energy. That means work it will get done to break these attractive forces, and whatever the energy is required to overcome these attractive forces, this energy it is used from the thermal energy, and whatever the thermal energy which is there into the gases along with the gaseous molecules in the compressed state, it will be utilized to overcome the attractive forces between the gaseous molecule, so that what we are getting here, we are getting the cooling effect after expansion of the gaseous molecules. Okay, we'll see its principle. It is used Joule-Thomson effect as the basis of the liquefaction of the gases. So what happens when the compressed gas is allowed to expand into the vacuum or the region of low pressure, it will produce the intense cooling. Why it is providing the intense cooling, I have explained right now. Next, in a compressed gas, the molecules are very close, okay, as they are having the together, and the attraction between them are appreciable. Okay, we have discussed this. As the gas expands, molecules they will move apart. So for the movement of the molecules apart or away from each others, in this process, intermolecular attraction must be overcome. That is, you need to provide, or you have to overcome the whatever the attraction is there between the gases molecules, and to overcome these attractions energy is required, and this energy is required, energy it is taken from the gaseous molecules itself, and this is in the form of the thermal energy. Okay, as the thermal energy from the gaseous molecule it is utilized to overcome the attraction between or intermolecular attraction between the molecules. What will happen? We are getting the cooling effect. That's why we are getting the intense cooling. Okay, this is Joule Thomson effect, and exactly this mechanism, this concept, this principle, it is applied here into the Leeds method. That's why the compressor is used in this Leeds method, so that this compressed air it is passed through this glass tube. Okay, understood why compressor is used and what is Joule Thomson effect and what happen when the gaseous molecules they will get expand from the compressed gas. So the compressed, the pressure it is collected here, and with the help of the compressed, high pressurized compressed air it is passed through this tube. When this compressed gas is passing through this tube surrounding to this refrigerating liquid, again as like in the Faraday's method, whatever the ice crystals which are placed surrounding to that glass tube, here also the refrigerating liquid is placed. So that refrigerating liquid, what will happen? It will carry the cooling of these gaseous molecules. Again it will absorb, again it will absorb the thermal energy from these gaseous molecules which is remains from the Joule Thomson effect or from the compressor or after expansion of the compressor gas. So here also we are trying to decrease the temperature. Okay, at the refrigerating liquid which is provided surrounding to this glass tube. Again, when this glass air it is passing through this spiral tube, and here at jet wall, okay, or at the narrow jet it will get expand. Here the opening is also narrow. Here again friction takes place between the gas molecules and this narrow opening. Again to get expel from this narrow opening or to overcome this friction, again work it will be done. Again to overcome that friction between the gaseous molecule and this narrow opening, again energy is required. Again it is utilized from the gases itself. Again it is utilized as a thermal energy. So what will happen? All the energies or whatever the thermal energy which is present along with the gaseous molecules, it will be reduced. Okay, so at the end, whatever the molecules we are getting here, these are less kinetics. Okay, they are having the negligible kinetic energy. They we are getting here. These molecules are together, and these molecules which are collected here in the form of the liquid air. Again, question will be in your mind that why this spiral tube it is provided. Okay, let's see. As these molecules of the gas, the air it is passing in the straight or the straight directions, either this gas molecule is getting any hurdle? No. As there is no any hurdle, the energy required is less. Okay, the energy required is less, and as here we are getting the hurdles, what will happen? The gaseous molecules they will get obstacles to get pass, to get run. The molecules they will get hit. As the molecules they will get hit here, friction will be takes place. As the friction will be takes place, its velocity it will be decreased. As velocity it will be decreased means molecules they will start to slow, and as the molecules they will start to move slow with the low velocity, they will start to aggregate. This will be the one concept. Second is, as the molecules they are attacking or the friction is takes place at this spiral tube, again to overcome that friction it is necessary to do the work, and it is the energy required to do this work it is utilized from the again thermal energy from the gases. So again cooling effect it will be increased, okay, in the Lenz's method. So at the end whatever molecules we are getting, these are in the liquid form. So how the liquefaction of the gases which is carried out with the help of the Lind's method or the Lind's apparatus by using the compressor, by using the principle or the basic concept, it is the Joule-Thomson effect. Understood the principle of the Lind's method? It is totally depends upon the Joule-Thomson method. It is quite simple, Joule-Thomson effect and how it's work, and on that basis how the apparatus for the Lind's method it is designed. Just I will read because already we have explained by seeing the picture. Lind's used an apparatus worked on the above principle for the liquefaction of the air. Pure dry air is compressed at about 20 atmosphere. Okay, that is with the help of the compressor. It is passed through the pipe cooled by the refrigerating liquid. Okay, we have seen the refrigerating liquid is provided to that pipe. The liquid such as ammonia. Here the heat of compression is removed. Okay, that is temperature is absorbed, that is heat is absorbed. That means heat of compression is removed. The compressed air is then passed into the spiral pipe with the jet at the lower end. The free expansion of the air at the jet result into considerable drop of temperature. Okay, is earlierly we have discussed in Joule-Thomson effect how due to the expansion temperature it will get reduced. The cooled air which is now at the bottom, sorry, now at about 1 atmosphere pressure passed up to the expansion chamber. The further cools the incoming air of the spiral tube and returns to the compressor. Okay, further cooling, how it is carried out, that is the work done, that is the friction between the gaseous molecules and that spiral tube. With this the further cooling it is carried out. Okay, next is the by repeating the process of the compression and expansion the temperature low enough to liquefy air is reached. This process it is repeated and at the end we are getting the liquefied air and it will be collect at the bottom of expansion chamber. See here, at the bottom of expansion chamber you are getting the liquid air, that is liquefied gases. Okay, this is about the Lind's method. It's a principle on the basis of Joule-Thomson effect and the apparatus which is constructed for the Lind's method. Second method is Claude's method, which is similar to the Lind's method. Actually, it is the third method. First is the Faraday's method, second is Lind's method, and third is the Claude's method. But this Claude's method, it is similar with the Lind's method. If you see its apparatus or the picture, it will be quite similar to the Lind's method. Okay, just only the one piston it is attached to the expansion chamber in this Claude's method. Okay, again pressure with compressor, this refrigerator liquid is there, pipe is passed through this refrigerator liquid, spiral tube it is there, that is air is passed from the spiral tube and jet and liquid. But here what will happen, one additional, after passing through the spiral tube, after passing through this refrigerating liquid through the spiral tube and the jet, narrow jet opening, till if the gaseous molecules they carrying the energy and they are in the kinetic energy forms, these are not cooled. So such types of the molecules which are from the expansion chamber, they will be get passed towards the again towards the compressor. Okay, that cycle will be repeated. But before this, in the Claude's method, he has attached, he has provided one additional portion, that is the piston. Okay, so what happened from this narrow jet, whatever the air it will get expelled, it will get passed into this opening also. Through this opening, it will reach to the pistons. So what will happen? When it will reach to these pistons, the piston it will move to and fro. Okay, as the expansion of the gas takes place, what will happen? These pistons it will be pushed. Okay, due to the gas, again it will get or enter into the expansion chamber. Again piston it will move. So that means what happened, due to this here, movement of piston is takes place. Movement of this piston is takes place. Again the movement of this piston is not with the aid of the external energy. Okay, it is just due to this air, whatever the air which is passing from this expansion chamber. With this only this movement of piston is takes place. Again, movement of piston, it is work. Okay, to move the pistons, to push the pistons, again work done is necessary. Again, for this work done, energy is required, and this energy is again utilized gaseous molecules itself only. So what happens? More work done it is carried out with the help of these gaseous molecules in the clouds method, in addition to the Lind's method. Okay, this is the just the additional provision or additional facility or additional portion which is provided in the clouds method as compared to the Lind's method, so that what happen, we are getting the more efficiency of the liquefaction of the gases. Okay, more amount of the gas it will be liquefied in the clouds method, that is efficiency it is increased as air expand and pushes back the pistons, just due to the movement of the pistons. And to move the pistons back and fro, the energy is required, force is required to carry out this work done, and this energy to carry out this work done, it is utilized from the gases itself. And here also cooling effect it will be increased, that is the construction or the apparatus of the clouds method. Principle is again same. The cooling is produced by free expansion of the compressed gas, but in addition the gas is made to do work by driving the engine. Okay, it is again similar to the Joule-Thomson effect. The energy for it comes from the gas itself which cools. Okay, that is to drive the engine, whatever the energy is required, again it is utilized from the gases itself. Okay, thus clouds method, the gas is cooled not only by the overcoming the intermolecular forces but also by performing the work. Okay, just additional work performance or the work done is carried due to the engine, that is the piston which is attached to this that apparatus. So what happened? Due to this, what happened? The cooling produced rate is greater than the Lind's method, and as the cooling produced rate is greater, we are getting the more liquefaction of the gases with the high efficiency as compared to the Lind's method. Apparatus again same, just we will discuss. Clouds use the apparatus as shown in the figure. Okay, pure dry air is compressed at about 200 atmosphere, similar to the Lind's method. It is led through the tube cooled by refrigerator liquid or remove any heat produced during the compression, similar to the Lind's method. The tube carrying the compressed air then enters the expansion chamber, again same. The tube bifurcates and a part of the air passes through the side tube into the cylinder of an engine. This is the additional facility, additional portion which is attached, that is from the this expansion chamber one tube, it is provided toward the an engine. Here expand and pushes back the piston. Okay, piston it will get expand or it will again get push back. This movement of the piston, okay, coming back to the point, and the expand, that is push of this piston, it is does by the air only. So thus the air does mechanical work whereby it get cool. So with this mechanical work which was done by this air only, and again due to this mechanical work, what happened? Cooling it takes place into the air. So what will happen? The air then enter the expansion chamber and cool the incoming compressed air through the spiral tube. Again that same what exactly takes place into the spiral tube. The air undergoes further cooling by expansion at the jet and liquefies. That is same as the Lind's method. Gas escaping liquefaction goes back to the compressor, and the whole process is repeated over and over again. That is until and unless we are not getting the more liquefaction of the gases, what will happen? That process it will get repeated. That means the pressure it will be get compressed, that compressed air it will be passed through that pipe, that pipe it will be surrounded by the refrigerating liquid like ammonia. Again that compressed air it will reach to the spiral tube. In the spiral tube work done will be takes place. Okay, again at the end the narrow opening jet will be there. Through this narrow opening jet what will happen? Air will be get expands in the expansion chamber, the which is get cooled, it will be get settled at the bottom in the form of liquid, till the some molecules, if these are carrying the kinetic energy or the thermal energy, again they will get pass into that compressor. It will be returned to the compressor. Again this compressor to the same cycle will be repeated in the Lind's method. Same cycle will be repeated into the Cloud's method also, but here one additional piston, one additional engine is attached to this Cloud's apparatus. That is, that piston, it will be move and it will be pushed back, and for that whatever the energy is required, whatever the work it is happening or work it will be done in the pushing that piston, it will be done by the gaseous molecules. And again, as the gaseous molecules doing this work, energy it will be utilized, temperature it will be utilized in that work done. And what will happen, more cooling it will be takes place in the Cloud's method as compared to the Lind's method. But it is totally depends upon the Joule-Thomson effect. Okay, thank you very much.